So we previously saw that determinant had this property of multiplicativity if one of the matrices was an elementary matrix or a product of elementary matrices. The next theorem that we're going to see says that in fact this holds even if the matrix, even if none of the matrices satisfy that condition. So in other words, this holds for all products. Whenever you take a product of two, these are square matrices of course, product of two square matrices, the determinant is the product of the individual determinants. Okay, we're not going to prove this fact in this course. The proof is right here in the notes. It's also in the book. You're welcome to look through this. In fact, I encourage you to think it through. All the individual steps in this proof are things that that are accessible to Math216, but it does take a little bit of time. Be a good practice read anyway. So this is something that is very surprising. We wouldn't expect this to be true. Certainly looking at the cofactor definition of determinant, you certainly wouldn't expect this multiplicativity property to hold. We are going to find a point of view, though, that makes this seem very natural. We'll see that in a few minutes. Okay. First, we get to a corollary of this, and that is that the determinant of an inverse matrix is the reciprocal of the determinant of the original matrix. And this is an easy proof to do, and that is if you want to show that two things are reciprocals of each other, you multiply them and show that the product is equal to 1. Right? Easy way to show that two numbers are reciprocals of each other. Well, by the multiplicativity property above, this product of determinants is the determinant of that product. And then, of course, a matrix times its inverse is the identity. And the determinant of the identity is 1. So, convenient fact to keep in mind, inverting a matrix gives you a reciprocal determinant. Okay, so we're going to take some geometric points of view on these facts here, and before we get into that, there's a reminder that I need to make for students. This is material that should have been covered in your single variable calculus course, but I'm aware over the years, I have become aware that not every course covers this following idea, and that is of what it means for a function to be invertible and how one can tell what are the conditions for a function to be invertible. So I'm going to make an abstract picture here of a function, a domain, and a target, and I'm going to, in the abstract, say that our domain has 4 entries and our target has 4 entries. Let's just say. Okay, so the idea of an inverse function is a function that does this. Right? So we're looking for, if f takes these points to these points, we want f inverse to undo that process. Okay. Well, importantly, in order for this to work, the function has to make what we call a one-to-one and onto relationship between the domain and the target. You have to have exactly this. So you can't have, and the arrow goes this way, by the way, there's our function. You can't have anything other than this sort of a thing. Now the lines might cross. Sure. Right? But importantly, what we need is for every output vector, there needs to be exactly one corresponding input vector. Of course, the reason you need this is you need for when you invert, you need for that inverse function to actually be a function. So I can't have any situations like, let's suppose my function looks like this. This wouldn't be okay. This function can't be invertible because, well, gosh, what would be f inverse of that? Nothing went to it, therefore there's nowhere for it to go. Okay. Likewise, there's a problem here. where does this go? Does it go to here, or does it go to there? So this point has too many preimages. This point over here has not enough preimages. So every point in the target has to have exactly one corresponding preimage in the domain. And the easy way that we describe this is with the words one-to-one and on-to, and I won't go into the details of those specifics of those words individually. Okay. All right. So with that in mind, let's think about some of our old facts about determinants and how can we think of them geometrically. So here is an old fact about determinants, that a matrix is invertible if and only if the determinant is non-zero. And there's a nice geometric point of view on this. Okay. So keep in mind that a matrix can be thought of as a function. And in particular, it's thought of as a function. We can think of what it does to the standard basis vectors, and then more to the point, what does it do to the cube that's defined by the standard basis vectors, and it turns that cube into, well, some sort of a parallelepiped. Okay, so that's one of our previous points of view on a matrix. And let's consider cases. I'm going to start off by considering the case where the determinant is equal to 0. Well, the determinant equaling 0 tells us something geometric. It tells us that the volume has been smushed. In particular, this parallelepiped is flat. Right? Okay, so the volume in there is equal to 0. All right. Now, think about the process by which we would achieve this. How would we take a non-zero volume cube and get it down, transform it down into something that has no volume? Well, unavoidably, if you take something with volume and turn it into something with no volume, you have to smush the volume. And so, for example, some point, let's say here, that point, an entire line of points must have been smushed onto just that one point. So that means that this function is not one-to-one and onto. It is not true that every single point has exactly one preimage. Here, this point's got a bunch of points that are the preimage. So it's not one-to-one and onto, and therefore it's not invertible. So what we see here is that if the determinant is not non-zero, in other words, if the determinant is 0, then the function is not invertible. Okay. All right. Now let's consider the other case. What if the determinant is non-zero? Well, if the determinant is non-zero, then that means that this parallelepiped here has non-zero volume. That means it's inflated. It has not been smushed. Right? Being as it has not been smushed, the function's going to be invertible. It's going to be one-to-one and onto. Nothing has been pushed onto anything else, and therefore the function is invertible. Okay. So it's a nice way to think about this relationship between determinant and invertibility. We saw an algebraic point of view on it previously, and I think it's nice to be able to take a geometric point of view. Importantly, notice that this geometric point of view comes from understanding matrices as functions. Right? We had to think of matrices as functions to be able to come to this conclusion, to be able to see this point of view. Okay. Ditto for multiplicativity. I can think of multiplicativity as a sort of natural, I'll say expected consequence of thinking of matrices as functions and determinants correspondingly as stretching factors. Okay, so let's think about this product of matrices AB. And keep in mind that if you take a product AB and multiply by some vector x, what happens to that vector x is the very first thing that happens to x is b multiplies by it. and then subsequently, after whatever the product is, bx, that then gets multiplied by a. Okay, so you do have to remember that the order of the multiplication is seemingly backwards from the order that the diagram looks. Okay. All right. Well, looking at just the matrix B, let's forget about A, let's forget about the product. Let's look just at the matrix B. The determinant of B tells me the stretching factor between those two volumes. Okay, now let's look just at the matrix A. What does the matrix A do? Well, it's going to take this parallelepiped and it's going to turn it into some other parallelepiped, and in particular the determinant of A is going to tell me that volume stretching factor. All right, so how much bigger is that volume than that volume? Okay, well, so what happens when you multiply two stretching factors? Well, if altogether here you've stretched by a certain factor, which we have, and if here you've stretched by a certain factor, which we have, then grand total between the two of them, in other words, in multiplying by that product AB, a grand total of which the stretching factor is the determinant of AB, grand total you have multiplied by the product of the individual stretching factors. So let's just think about this from a point of view of some numbers. If this stretches factors by a factor of 2, and if this stretches volumes by a factor of 3, well, no surprise, doing both together stretches volumes, well, first by 2 and then by 3, and altogether stretches volumes by 6. Right? Very natural that these things multiply. So it's a really interesting point of view. Again, if you take an algebraic point of view on this, it's extremely cryptic and opaque as to why in the world would this be true. But if you take this geometric point of view of interpreting a matrix as a function, then what had been algebraically sort of cryptic becomes geometrically very natural. Wonderful little point of view. Okay. Finally, this result that we just proved on the previous page about the determinant of an inverse matrix being the reciprocal of the original determinant, well, no surprise. However much volumes stretch by A, thought of as a function, well, A inverse has to return the volume to what it had been, and therefore has to unstretch by exactly the same amount, and therefore, said differently, stretch by the reciprocal of that amount. So, again, natural result.